Hey, hello there. Let's talk about today's Leetcoding challenge question. It's called the maximum width of binary tree. Given the binary tree, we want to write a function to find the maximum width of the given tree. So for a binary tree, each level will have some kind of notion of a width. And this question is basically asking us to find the width for all the levels in the binary tree and return the maximum number among all those widths. So how to calculate this width? Imagine that we have a binary tree looking like this, and every node in the same level, we're going to index those nodes starting from some certain number. And if there is a node missing, we reserve the index number for that position. And if we do this, then the width is basically the maximum index number for the very last node in the level. Subtracted by the first node in the level, the index for the first node in the level, and then plus 1. So let's look at example here. For the first level, we have just one node that's indexed 1. So we have 1 minus 1 plus 1. We just have the level with width 1. For the second level, the maximum, the rightmost node has an index value 2. The leftmost node have index value 1, so the difference is 1. We plus 1 to get 2. That's the width. For this current configuration of the third level, the last node have index 4, the first node have index 1. So we subtract the 4 by 1 to get 3. 3 plus 1, we could get the width for the third level, which is 4. Note that if we modify the topology, maybe move node 6 to the index 3 position, then the width for this very last level becomes 3. If we, on top of that, if we delete node 4, then the width is going to be 2 for the very last level. So that's pretty much how we calculate width for each level. We can, during the tree traverse process, we can just annotate the node on the same level with the continuous increasing incremental index numbers. And we also allocate the index for the null node there. So instead of index from 1 every level, we can use the trick that we do serialization and deserialization between tree and array. That is to use the index number to figure out, do a little bit arithmetic to figure out the index. So for the first node in the first level, if we index that with 1, we can index this number with this node with 2, which is 2 multiplied by 1, and this node will be 2 multiplied by 1 plus 1. For this node, the first node on level 3 is going to be 2 multiplied by 2, and so that's 4. Basically, the node's value here at the index that we can do. So if we do Dfs or Bfs search, when we process a node, we know the index for that node, then the left and right children's index number, we can just do arithmetic and figure that out. Yeah. So in short, it's very easy to apply Bfs search to solve this problem. We're going to explore the tree level by level, and each time when we look at a particular node, we look at two things. One is this node, and we use that to traverse to the children. The other thing is the index number, because we're going to calculate the left child and right child's index number based on the parent node's index number. And when we process a level, we're going to keep track of the minimum and the maximum index number and calculate the widths for every level. In the end, we're just going to take the maximum among all the level widths. So that's to solve it by Bfs. It's pretty intuitive. So let's code the solution up. So we're going to use a variable to keep track of the maximum widths. And to do Bfs search, we need a queue. Initially, there are two things, the root node and also the index number, that's 1. So when we explore the two children's, we're going to use this index number to figure out the children's index number. So we're going to enumerate over all the nodes inside this level. Node index equal to q.popleft. And so what we do is to actually for each level we can directly calculating the widths. That's going to be level width. It's going to be the index for the first node and the index for the last node. We take the difference and plus 1. I don't need this. So that's the level, the width of this level. We just try to update the global maximum width with this new width. So after we've done that, we make sure that we push the children onto the queue and also annotated the children with the correct index number. So I think that's pretty much it. Let's just read through the code. Oh, I have to initialize this to be initialize this to be 0. Yeah, so let's talk about the code. We have a while loop that's indicative of do we still have a valid level we can traverse. If that's the case, we definitely we just want to look at the first node and the last node's index number. Take the difference between those and plus 1 to get the current level's widths, and we use that to update the global maximum. After that, we pop all the nodes out of this current level. So this for loop just tells us how many nodes we have to pop in order to fully process this current level. Whenever we pop a node and its annotated index number out, we look at the left and right. If we have a left, we push that left child onto the queue together with the correct index number. Otherwise, we do nothing. We do the same thing for the right child. So after this for loop, we should be able to flush the queue with the nodes with its annotation in the next level. Yeah, so that looks like it. Let's see if it works. So this is the Bfs Search solution to this question. It's pretty straightforward. You could also solve this with a Dfs Search. So to do that, when you traverse, you definitely would keep track of this index, because you no longer have this level by level kind of notion there. When you traverse, you have to keep track of which level this node belongs to, and maybe use a hash map to store level to min index and max index. You have to keep track of that, and in the end, you just enumerate over the hash map to figure out the difference, the maximum difference between min and max plus 1. So that would do as well. Let's actually just code that up. So let's call this Bfs. So let's code a Dfs as well. Of course, we need a similar construct. We need something to keep track of the maximum width, which is initially 0. And this time we need a stack because we are doing Dfs, which is going to be the elements on this stack is going to be 3 things: the node, the level, and the index. So let me just comment here: node, level, and index. because in Dfs Search you no longer have the notion of you cannot get the level by looking at the loop there. So you need to explicitly handle the level there. So looping is similar. While stack, what we're going to do is to pop out a node from the stack. Node level index equal to stack.pop. And once we pop this, we will try to update this hash map with level to the min-max mappings. So of course, one thing we need to handle is to initialize this key value pairs if it's not there. So level, we call this level min-max. So if level not in level min-max, then what we do is to initialize this with a tuple. I would just take the maximum as the minimum and minimum as the maximum. So I would define those somewhere up there. So that's the initialization. If I haven't had any kind of min-max statistics about this level, I do this. So actually I can have this to be 0, right? Anyway, this should be fine. Otherwise I would try to update this. 0 is the let me annotate here. Level to min index, max index mapping. So the first element is the min, so we take the minimum between the current minimum and this index number. We do the similar update for the maximum. So after we've done this, we can that means we have processed this node. Then we want to explore the children of this node. So if node.left, again we put 3 things onto it this time. Left, and the level is gonna +1. The index is the similar update rule. We do the similar work for the right, except we have index to be 2 multiplied by the current index +1. So that's by doing that we populated the min-max. In the very last, after we annotated each level, so each level is going to be annotated with the min index, max index. We can just enumerate over those tuples one more time to figure out the maximum differences. So we're just going to do one more loop for min index, max index in sorry, I think I need a this is not numpy, this is not pandas, so I have to do, this is a method. So I will just try to update the maximum width with the difference between min max index +1, and in the end we should just return max width. So with this I can try to see if my function works, the Dfs search. Does it work? Oh, I need comma. Not okay. So I'm outputting a extraneous big number. So what's the reason for that? Did I overflow or something? This is huge. How do I solve this? Okay, let's do a better initialization. So for level I, the possible maximum is 2 to the power of level subtracted by 1. The minimum is 2 to the power of level subtract 1. So I can, instead of doing that, I can use the information about level to initialize this. I think it has to be the min-max handling that's a little bit problematic, so that we got this really huge number output. So I'm going to have the maximum to be small, which is level -1, and this maximum should be this. With this better initialization, I think it will work. Let me try to grab another example. How do I configure? Okay, this. Does this work? Oh, okay. So this has to be. Oh, this is only the last level. Shit. Anyway, let's try if it works. Let's accept it. Okay, it's the initialization. All right, so that's the question today.